start again. 要讲，我跟体育室合作了2年，我至少已经合作了4、5年。从这个NCK with a good sports technology, probably is the best sports technology in Taiwan. It's about we start from year 2018. Start from there，所以我带团队做到现在。I lead a team about 15 professors and students. Students about 30 students. 一些怎么说呢？一些心理系老师都有。And 2 years ago, I started to work on our sportsmen. Sportsmen 就是我们的运动员。So this week we have a soccer team in CKU. We already there's a right now we are competing so all the collect the points 就积分然后今天打到前4名。We beat the last year of the top 4. We one game is equal, 2 games we win. So today 11 o'clock we'll pick is the number 1 team in Taiwan. 11点我们有一个 game 要比赛。So we will find out in NCTU this year our several sports team will be on the top. Taiwan. 所以 top 不是只有是一起球队，是跟那些体育学校是竞争的。所以你在校园里面可能会发现，我们校园里面开始有一些190公分的人然后女生有180几公分的女生在校园，跟人一样。他们很厉害他们不会，他们是国手。They are national team member. 因为我去争取那些名额进来给学校，然后他们应该说他们不止运动很厉害，他们那成绩，相当就是还是有办法生存下来。所以成大在这方面当时我有在耕耘，让它越来越强，然后会就希望这样跟 I learned that from in United States, like Stanford University. Stanford University, they are not only good at technology, they're also good at sports. 他们有些奥运选手，所以我们是希望成大的多元发展。那这主要是校长愿意支持我们，我们校长支持往这边。那今年从上学期开始就有混合大队接力。这次有混合大队接力有包括不简单，有80个 team。要想一个 team， 一个 team 有20个选手，混合就男女混，那80个 team 就有826，就1600个大学生。那我们研究生好像比较没有在动这一块。 别的方向，是靠自己。
选手不简单哦，他们还要练球。你应该我们上里面可能有些那选手有一些是国手，还有些是我们的一般的那个团队是还有我们一般的学生。希望成大可以多方面的发展。
啊，那足球真的不简单哦，他们那些大一、大二那些以大一、大二为全线踢到，我刚刚讲是大概去年前4年有就一场平分2场赢他的，那今天这是积分，那下半年下半学期的样子才会有那个比前4名，那再来就有篮球赛，还有我们女篮也不错，我们女篮跟女排都是一起抽的，一起是跟体育学校打的体的这样子。we start here. Before I continue talk about LDA, I just briefly talk about SVN. So I said SVN compared with LDA, the two different things. So 看一下没有 two things. One is I call margin. So the purpose, actually the purpose is this one. I already teach you this one. This one is purpose. What's purpose? The loss function. So that's the sum of square difference or mean square difference. This is the other margin. Sorry, the other regulation. So both together is like a branch. So the purpose is that we hope we reduce to have a lower variance and higher accuracy. So we hope either this one or this one, not this. This is the high variance. It's not good. This is our purpose. So this is the graph. So this consists from SVN. So I already give you the lecture. So what's first of all, what's the margin? So LDA in page 16. LDA is this one. Two classes. I use LDA to separate both LDA linear, but that's not good enough. So the other way is margin, this one. So we hope we try to find a line, but not only the line. We hope two classes can separate as away as possible. So that's the margin. We hope. So this, the first one, if the line is this one, in this direction. The other is the line is this one. We will find this line is large margin. So this line is the line. So and this one is the rotation, the W. It's a W. W control the rotation of the line. So we will find this is better than this one. They include a large margin. So SVN, the first important one, they have a margin. The second one, I try to say is Lagrange. Find the Lagrange. This is Lagrange. This is Lagrange. Original function plus one more constraint term. This constraint term we also call regularization. The same. So we have one more. So back to here. So we include one more term. This term is a regularization term, also called constraint term. So this result is big，就这样。所以那个 SVM 的好处就刚刚这两个好处，比刚 LDA 更好。那当然中间还有一个是 one more thing 是它会做非线性的分类。刚刚讲是线性的哦，那它会做这个非线性。它实际上不是做非线性分类，是 SVM itself actually is a nonlinear separation. No, actually not. What they do is that they try to project to higher dimension. In higher dimension, each point more sparse, and then do the linear discrimination. The SVM actually, the concept is a non-linear separation. No, the concept is that this try to project to higher, we project to higher dimension, so that each point more sparse, and then do the linear discrimination 这样子。那所以重点是它怎么去找到这个 higher dimension。那这个是它优点，是它缺点。刚讲是两个基本的观念，就是意思说你先 project 到 ，if you project to higher dimension and then you do margin, you do the branch optimization. So all the process is that we might try to find this phi is we project to higher dimension. So this optimization will help you to find this phi. This phi is project to higher dimension. So this is advantage 它的好处 but also it's disadvantage 这个是它的坏处。Why? Because they don't know how high dimension you want to have. 他不知道要投影到多高，所以他不管，他就 so in SVM they project very high dimension. That's not good. It's not good. So deep learning improve this one. Deep learning says, oh, that's not good. We don't need to project so high dimension. Each time we just project to a little bit higher and try to separate it and project to the other space without separate. So deep learning, why is deep? Because why they need activation function. So in SVM, this activation function, like in higher dimension. Okay, but in deep learning, you say, oh, you don't need to project to such high dimension. You just use a small, a little bit high dimension as activation function. That's it. This is SVM one. So many deep learning, the concept is based on the machine learning. So we back to here. So again, our purpose is try to find L. No, that's wrong. Our purpose is try to find W in order instead of L. So W is your projection line. So back to here. So our purpose is try to find W instead of find the L. So W is the rotation vector is important. And before I talk about the optimization, I will talk about for each point X. So X is each sample point. So each sample point in 2D, we try to find the best W in the projection line W. So that's meaning 2D sample X, we project to the line W. Our projection result is Y. So Y is 1D, X is 2D. So in order to find Y, we need to find W. So this one. So this one is we try to say this one. Okay. So next page. So actually, page 8. So our purpose is this one. Then again, all the classification, so the layout, all the classification is based on loss, optimize the loss function. So loss function is the most important one. Loss function. So in this case, the loss function on this one. The loss function is what we try to have this is a theta is meaning projection. So what we want to do is this one. if we can project on this one, okay, so our 1D or low dimension, I say 2D project on 1D, 4D project on 3D. So lower dimension, so both Gaussian model, the mean value M1, M2 should be separate as bigger as possible. So we hope M1 minus M2 is bigger. Standard deviation S1 plus S2 is smaller. So we will try to optimize, try to find the maximum value of this Jacobian equation. What's Jacobian equation? When you study a paper, they just say, okay, in this result, I use one Jacobian. Optimize the maximum value of Jacobian or minimal value of Jacobian. Optimize the Jacobian and get a result. 什么叫 Jacobian？ 你常会遇到的问题读 papers 哦。那 Jacobian 你不要被它欺骗了，没有，就是一个 polynomial， 就是一个复杂的一坨的东西，一坨的数学式，它把它当成是一个 Jacobian。那你 Jacobian 像这个数学式，就是这个数学式，就是要找 W， 就这样。所以你把它种成一堆，最后这个最佳化这个式子，那你要找是找 W。So in this case, actually, first of all, in the low dimension Gaussian model here, we try to find maximize this Jacobian matrix. The Jacobian matrix, its nominator term is we want to maximize the nominator term, minimize the standard deviation. 是这样。所以我们目的要找出最大值，这个 Jacobian 的 loss function 最大值。当你把这个 loss function 分子跟分母颠 if you inverse the numerator and denominator will become minimized. 相同。Okay, so what is the projection mean? What is the projection standard deviation? It's here. Okay. So if the 2D sample, each one is xi. So we have two classes. One class we call H1, the other class is called H2. So if the two classes, for example, so if H1, 2, so X1 here are the class 1. So we have a summation all the samples in class 1, cluster 1. Of class 1, we will find the mean value M1. So M1 actually, sorry, is this one. Mean value of cluster 1. The red one is the mean value of cluster 2. So here, so the equation, this one, we find mean in 2D and Ni, N1, N2. Okay. And what they try to explain to you is that in 1D mean equal to 2D mean directly project to 1D based on W. 比如说，这里要证明 they want to prove you is that 2D mean equal to 1D mean equal to 2D mean directly project to the W space, the same as this one. This is sample. Again, if this is a 2D mean, if you can find a W projection line, this W become 2D project to W become 1D mean. 意思是说这个2D， 你只要找到这个2D 的 mean， 那直接投影到 1P， 那这个 mean 就是它的 mean。You don't need to like a 1D, you don't need to picture it again about the mean value based on Y. No, you don't need to. You just in 2D, you try to find average value, the mean value, and based on mean value, instead of all the samples, and you can try to find the projection W. That's 1D mean. Okay. So the equation here. So that's just the left for you. So that's meaning 1D mean equal to 2D x times W project times inner product. Inner product meaning project on W in total have a number is an N. But W is a constant term. So W can try to be separate from the mean value. So the result is the 1D mean equal to 2D mean. The jet on W vector become 1D mean. So this equation. So will become this one. So this meaning in 1D mean 1 minus 1D mean 2 equal to 2D mean minus 2D. Sorry, cluster 1 in 2D minus class 2 in 2D. You project on W. So you will try to find W. So this one will be put here. Because you know it's 2D. Then it's still 2D. You don't know 2D. Right? But you try to find W. W you don't know yet. So you just based on the 2D. Based on the 2D. W is the value we try to find. Okay. So this one is here. So even nominator 你的分子形式 you can find nominator. So how about this valence in denominator 这个 valence 这个 now valence is the same. Valence is the same as a 2D this 2D valence. 2D valence. And next page will tell you. Sorry, this one. In page 10 will tell you this one. So I just 2D, right? 2D in 2D. There's a valence. So valence is suppose S. So if a Gaussian distribution 1 valence for Gaussian distribution 2. This one, both two, you cross together will become this one. And SW equal to this one. Meaning the same. Meaning is in 2D valence, you can direct project to 1D, the same as the matter valence. But 1D valence equal to 2D valence, the vector actually project to 1D. So because this SW is this. SW is to be mean. W is W omega is the direction vector. So this equation becomes this equation. This equation you want to optimize. You try to find the maximal value of this loss function equal to this function. So this function is in the denominator term. SB is between two means in 2D. In the denominator term, the within what? Within the each valence will be as small as possible. So SB is here. SW is valence is here. So this equation equal to both block. 这个 equation 就变成这两个，用这个。So our purpose is to try to find the maximal value of this Jacobian. Yes. So how can we find the maximal value of a Jacobian? Easy way, just do that. We try to find W. That's meaning we just do the derivative of W. 我们要找最大值嘛？那最大值，因为这是一个二次曲线。W is a 2-degree 2 order， 就是 2-degree 的，对，要想最大曲线。So our purpose try to find W, but this is second order 二次，所以我们就微分。微分以后呢，我把数学式写在这里，就微分程式啊，因为还有这数学式 有分子跟分母嘛，所以你把这数也是带进去，就会发现 this is the result of the derivative of this one, the result. And we will find, see this result, this one, equal to Jacobian. This one equal to Jacobian. Because we try to find the maximum value of Jacobian. So this will become, we try to find one maximum value here. So assume this value, this one, equal to lambda. So this equation become this one. This equation become this one. So we have lambda. Lambda is this one. Lambda times SW omega equal to SB omega. And we will find, if we shift SW to the other side, we will find this one is the eigenvector, eigenvalue. It's amazing. Okay. So I always told you, when we try to find the optimized result, optimize this solution, sometimes SVD is very powerful. So in this case, you will find out, okay, with derivative of this Jacobian, we will find this format. This format is a constant times SW times omega equal to SB times omega. We shift all the input, we shift all the input together. So this will become SB divided by SW, this one matrix, omega. So this one equal to omega equal to eigenvector, lambda equal to eigenvalue. SB divided by SW become matrix. So that's meaning the answer is you try to, based on this matrix, you do singular value decomposition, become eigenvector times eigenvalue times rotation matrix. The matrix is the other eigenvector, become this one. 这变成 eigen 的东西了。所以答案就是说 your answer is ask 2D information you directed to SVD and you'll find you got eigenvector matrix eigenvalue, and because the solution try to find maximum value, so that's meaning the maximum eigenvalue corresponding to eigenvector, that eigenvector is your answer. Okay. Before we talk about the optimization, right? We use SVD, we try to, for the camera calibration, right? Camera calibration, we try to find is that the eigenvalue close to the zero. That's your corresponding eigenvector is your answer. In camera calibration, we try to find the solution. The solution is that we try to find the eigenvalue equal to close to the zero, corresponding to eigenvector. That's your answer. That's because the result is closed form solution, so equal to zero. But here, no. Here is that we try to find maximum value of Jacobian. That's meaning we try to find the maximum value of eigenvalue corresponding eigenvector. That's your answer. 这样就结束了。So your answer is here. Eigenvector. So that's done. So when we try to find the linear discrimination function L is equal to, we try to find the rotation vector W. How can we find rotation vector W is equal to based on this one, between and within, based on this matrix. We try to do SVD and try to find the maximal value or eigenvalue and then corresponding eigenvector as your answer， 就解出来了，这样子，这个忽然之间结束了，这条线就被你找到了，这条projection line就被你找到了，这样子。那你不要小看这个。So the same, the purpose in this class I teach you about camera calibration, teach you how to optimize the solution. The purpose I try to teach you LBA the same, is try to teach you how to optimize this Jacobian solution. The purpose I teach you the Fibonacci next week. Try to teach you the optimization of head, the loss function is very important. 所以研究生还是脱离不了数学，但是我说我们的领域，我的领域，就你们在学这门课，我们不要玩太难的数学，太难数学不是我们要玩的，我们是玩应用数学。我教你所有的应用数学就是这些东西。那你大概你如果往 deep learning 走，你如果往 computer vision 走，最难的数学就只有这样子而已，不会再更难了。这样子啊，只是我跟你讲 deep learning 的那两个数学式，就 close entropy 啊，跟 mean square error，它有一些变形，这样子，它不会太难，一般人不会太难，因为我不玩数学的东西，可是你要学，为什么？为什么你要学这个 loss function？ 因为你可能会稍微改变它的。我简单讲啊，就你们研究生在做研究的时候，你读这篇 paper 它用这个 loss function， 你读另外 paper 是用另外一个 loss function， 那你们能不能把，因为你现在以 A paper 为主，那 A paper 你要改它，那 A paper 的 loss function 觉得B paper 的 loss function 更好。那你有办法把 B paper loss function 拿来取代 A paper 来做，就这样子，你可能更好。但是重点是你会不会把 B paper 的 loss function， 也就意思说你 B paper 的 loss function 你看得懂 ，A paper loss function 你看得懂，但是你要把这个取代掉，你会不会用？会不会取代？这不难，但是你会发现。还是要有点基础的。我讲说你还是有点基础，不然你直接拿用你用不出来哦。我的建议是学生还是跑不出来，因为你的两个 loss function， 因为你的 model 可能不一样，然后你要学会这个。就我教你很多最佳化，因为你是研究生，我大学部就没有教这个，研究生很多都是要学这个最佳化的过程，这样子，我帮你整个整理起来。OK， 这边有教完，所以。complete the work about the LPA. So the major purpose is try to optimize this one. Okay. 但是你如果这个来讲是用 gradient descent 来做，在那一边是用 gradient descent 来做。Okay. 那我这个教完。Stop.